Welcome to Tic-Tac-Toe the Hard Way, the podcast in which a writer and a software engineer train an AI to play a simple game.
And take a hands-on approach to exploring the very human choices that go into training a machine learning system.
Alrighty then, let's get into it.
Okay.
Hey David, how did the training go? I hear we may have a machine learning agent to talk about today.
Hi, Yannick. We may. We may indeed. So, things trained.
Excellent. I do know that you trained a couple of models, and we'll be getting into those in a bit. But before we talk about that, I know that transforming the data into something the model could learn from is something you had a few challenges with. And I was wondering if you could tell us a bit more about how that went.
Well, a few challenges. It's very, very kind of you, Yannick. Most of the challenges were uninteresting because I'm not a very good JavaScript or Node programmer. Hesitant to even use that word, as I should be. So it was just every conceivable mistake that one can make outside of machine learning, and that just takes me a long, long time. And then I eventually was able to generate games, generating them randomly, which means that my program starts with a new game, and it randomly picks a number between 1 and 9 and puts the player's mark in that, and then the player switches, and it picks another random, and it puts a mark there, and it looks to see if anybody has won, and it keeps going until somebody's won, or the game is, the board is filled up and it's a tie. And I generated a whole bunch of games that way, 10,000 ultimately. There were some conditions on these games, though. I only saved games that had winners. So if a game ended in a tie, as we had discussed, we don't want to train the system on how to tie. We want it to win. So only games that had winners, I kept track, of course, who won the game. That's part of the data. Is it X or is it O? And did X go first or O go first? And that sort of thing. And so, I ended up with 10,000 games that had a winner. Some were won by X, some were won by O. And these games consisted of a bunch of moves. So, that's what, so I had stuff to train a model on.
And what were some of the challenges you ran into when sort of translating the data you generated into sort of the format needed for the model?
Well, so it was generally made a little bit easier by the fact that we had agreed, in other words, you had explained, what the data representation should be for each board. Each game consists of moves. Each move consists of a board that the player sees and the move that the player made, and where the move was represented as the number of the square that the player put an X or an O in, depending. So that was not the hard part. The hard part was, aside from the, sort of uninteresting node errors of an amateur programmer, the hard part was trying to get some confidence that the games that I generated actually were right and proper. And I had done it right, because there's lots of ways I could go wrong. I could switch around the X and the O's, who's playing. I could not be getting all the games that have winners and the like. And for that, you suggested that I write something that in the professional world would be called, I believe, a unit tester. Is that right?
Yep, which would be sort of a little program that you can write that runs small tests on maybe the data that you're generating so that you can sort of validate it.
Yeah, so I did that. And it did things like it looks through all of the saved games, which are only supposed to be games that have winners. It checked to see how long games are, because if you have a game that's 3 moves long, you can be pretty confident that that's a mistake. And so it passed those sorts of tests, which is quite reassuring, actually, even those simple ones. So
yeah, and we should say that the reason we went down this path is because you had started training your models, and it basically wasn't working. So the models weren't learning pretty much anything. So the question became, why is that happening? And as is common in machine learning problems, you need to go back to the data and sort of debug that data, which is a huge part of the machine learning training process. So finding ways to gain confidence that the data that you're feeding it is the correct data is pretty critical.
Yeah, this was a really, really... It was a really, really annoying. I could not figure out why the games that were being played were all wrong, because the data looked good. And I spent a long time. I spent days and days and possibly weeks and weeks trying to figure out why this was not working. And you spent about 4 minutes when I finally called you over in my shame and anger at the computer, and which means myself. I finally asked you for help, and you looked at it, and in your very perceptive and kind way, pretty quickly realized what the error was, and it's a somewhat embarrassing one.
So what was the error?
So the information that comes back when you ask the system to make a prediction, to give you the move, the information that comes back is a one-hot array, which we talked about last time. As you figured out, I was representing the data one way and interpreting the results the other way. So I kept getting, in every case, not only did I get the wrong number, the wrong square to play, but there was, in fact, and I actually sort of enjoyed this, a pattern to the wrongness, because they were like mirror image numbers. Where it should have been a 1, it was a 9. Where it should have been a 2, it was an 8. And that's, it was so frustrating for me. The result was actually sort of deeply satisfying.
It sort of led you to that in the game playing environment, it would put the mark sort of in the opposite place from where the model had actually said it should go because of that mismatch in data representation.
It was sort of neat, actually. I know you'll contradict this. It was a really pretty dumb mistake.
It was a human mistake. And you're allowed a few of those. So that's great. It's great to hear sort of us getting past that.
Oh, yeah.
So I'm curious to hear more about how the models did.
So the first model was one in which it only recorded into the data set unique boards.
What do you mean by unique boards?
So it's going along generating these random games, and the games consist of boards with recommended moves. If the random generation created a second instance of a board that had already shown up in the data, then my model, I just threw out that data. I didn't record a second one. So there was only one board in the entire set that had a single mark in the first square, and likewise for far more complex boards. You suggested that I do this.
Yes. Why didn't you tell us about the second model, and I'll say why you ended up doing this one.
Okay. So the second model just was random generation, and it accepted all boards that were in a winning game. It didn't throw out any of them. And so there'd be multiple instances. I played 10,000 games. There'd be many instances of the same board showing up. And frequently, I assume, because it's still random, the move randomly generated for these different boards could well be different for all the boards or some of the boards because it was random.
Yeah, essentially you had, for any given input, there'd be multiple answers as to the correct things to do. So the reason I had you narrow it down to unique things is, again, because at that time it wasn't working. Nothing was learning, and we had to find out why. So simplifying the problem to just unique pairs of input and output just made it that much easier to debug, sort of to discover the issues that we had discussed previously. It was a useful approach, like how do I make this easier for myself to trace what's going wrong before I sort of move forward with more training.
Yeah, I mean, it certainly limits the set of things that you can look at. Although, in terms of actually trying to create a model that's going to win tic-tac-toe and crush the opponent as often as possible, it's clearly not the way you'd want to go, because although it's picking a move in a game that was won by one of the players, that move may not be the best move in any sense.
Mm-hmm.
So there's reason to think that it's not going to play very well. I was surprised actually it played this well. It actually worked.
How well did it do?
63% of the time.
So 63% of the time it beat a random player?
Yes.
I'll just remind the audience, the random agent just looks at the board and looks at which spaces are free and picks one at random to put it in there.
Yeah. And so maybe it's not that much to crow about, because it's like literally like playing the stupidest possible human.
Mm-hmm. But again, to validate that it was learning something and it was learning to do something correctly was pretty important. I'd say one thing that stood out to me when we got to this milestone is that it wasn't getting disqualified anymore, because before this, when it just wasn't working, it was like constantly getting disqualified. It would play a mark in a cell where there's already a mark or that kind of thing. And this was sort of that first proof point that it could learn something approximating the rules of tic-tac-toe.
I'm very glad that you had me do this. And the fact that it, quote, learned the rules, or as you put it, approximated the rules, is actually pretty remarkable. We didn't tell it what to do, and it learned that.
It figured it out. It learned it. And there were no constraints in either the viewer or the training process for the agent in terms of where it makes moves.
Yes.
So it's a good start, and it's very impressive. And I'm proud of you.
I'm a little proud myself, although, again,
Yeah. It's a modest start. It just suggests we're going in the right direction. So going back to that second model, which did see lots of examples of what to do for a given input board, how well did that do?
So that one I harvested, so to speak, or generated 15,000 moves. They are non-unique, they're repeats. And that one, it won 87% of the time against a random agent.
Ooh.
Uh-huh.
Nice.
Yeah.
Nice. 90%. Like, it's almost an A.
It's a pretty
90%.
solid B+. Pretty solid B+.
Yeah,
So.
very solid B+. You've conquered Tic-Tac-Toe.
Yep.
You have a little bit of a ways to go, but it's definitely playing much, much better than random, right?
Yes. So that first model is in the, if you've got a kid in Little League or whatever, it's in the good swing sort of category.
Mm-hmm.
And this one definitely will beat random quite handily. What it will do against
training wheels are off.
How it would play against an actual human, or more interesting, how it will play against your model, which we are getting to in a couple weeks maybe. That will be very interesting to see.
Yeah, indeed. Cool. Are you pleased? Are you pleased with the outcome?
Pleased enough. Pleased primarily because I went through the whole process with a lot of handholding from you, but went through the whole process. I have a sense of what that very simple process is for a game like Tic-Tac-Toe. And, it got a reasonable outcome. I think there are other things I could have done in generating the data that might drive the accuracy up.
Yeah, I'm curious what your thoughts on that are. How would you look to improve this model if you could?
Well, so right now this model is generated purely randomly. But if you were a human player and you're facing a board and it's your turn, the first thing you would do is check to see if your opponent is about to win. And then you would block it, immediately block it. Or I guess maybe the first thing is actually that you would check to see if there's a move you can make that would end the game, you would win. Just sitting there waiting for you. And you would take that. And the generator that I wrote does not do that. But it could. In which case, I would assume that it would be a better player and thus would win more games.
Yeah, I think that's a reasonable assumption. Like, it would have better training data to go off of that sort of has encoded some heuristics or some strategy for playing Tic-Tac-Toe. And we'd hope that it would learn to pick those up and do even better against a random agent and possibly well enough against a human, should it ever meet one.
The reason why it would do better, I'm just going to state the obvious, it should do better, one would think, is that if you and I are playing as humans and I don't notice that I could win this turn and I play a different turn, that gives you more opportunities to win. So I'm creating an environment in which my opponent has more possibilities to win. And if I do that in generating games, then I should decrease the number of wins. I don't know how we would know this, but I'm curious about if we did that, or if I generated data that looked ahead to see if there's an immediate move to take, whether the system would learn to generalize that. I'm not sure exactly what I mean, but if I block you, you got a diagonal going and I block it, and that's a good move for me to do. Whether it would eventually come to realize that it's not just diagonals. It's any time that there are, quote, 3 in a row. But I think this doesn't make sense because it doesn't know about 3 in a row.
But it might be able to learn that or encode that pattern. And now you're in a great place to sort of ask and answer that question by doing experiments. So you have this current model, which is 87% win rate against a random agent. You could generate a data set that only does the quote unquote smart thing when it's a diagonal and see how that changes the win rate. And then you could generate another data set that does it all the time. In the data set you generate, it does the smart thing regardless of whether it's horizontal or vertical or diagonal. And you could compare the two. You just run your training thing again and see which does better. And then that will give you a bit of a sense of what the model is able to pick up.
That's a really interesting idea.
Yeah. You have this baseline, which is a great place, and you can see if you can improve on it.
And even if it did learn to generalize from, I only train it to look for diagonals, and it starts noticing it everywhere. As a human, what I want to say is it figured out to do 3 in a row, But because we're giving this data in one dimension, it's just a string of 9 characters indicating who owns the square, if anybody does. It would be sort of, anthropomorphic to say, oh, it's figured out 3 in a row.
Maybe all of this is anthropomorphic, but if it does the behavior, then maybe it's figured it out. If it walks like a duck and talks like a duck,
yeah,
maybe it's a duck.
I suppose it walks like a duck rabbit and quacks like a duck rabbit. I think we don't want to go down this.
It's true. Philosophical debates. But I think it's great that you have a working model and you have some ideas for experiments you want to run. And running experiments is a big part of machine learning. So if we were really trying to pursue the best tic-tac-toe agent we could, we would definitely go down this path. But since this is really just a precursor to playing tic-tac-toe in that more advanced game, we can sort of put this to the side until you have a bit more free time and sort of look ahead to playing our next game. But before we get to that, we should obviously pit our 2 things against each other. And I haven't had too much time to talk about what I've been doing. So I think on our next episode, I'll try and introduce the audience to the reinforcement learning driven agent and talk a bit about that, how that works. And we can see how well it performs against yours.
Yeah, no, I'm looking forward to that because I want to know how reinforcement learning works.
Excellent. You've been listening to Tic-Tac-Toe the Hard Way with your hosts, Yannick Asogba and David Weinberger. This is a production of Google Pair, with thanks to Rebecca Salois, Eric Johansson, mixer and editor Brian Gordon,
and the entire Pair team of developers, researchers, designers, artists, philosophers, and more. A special thanks to Nikhil Thorat, who created the music with help from AI by Google Magenta.
You can find links to code and more in the show notes and at our website, pair.withgoogle.com/thehardway. Once again, that's pair.withgoogle.com/thehardway.